Hey, this is Peter, and today I'm going to talk about our first Encraption lab where we turn a Caesar cipher into a Vigenère cipher. So as you recall, Caesar cipher is a monoalphabetic, a single shift cipher, and Vigenère is a polyalphabetic cipher where we use the key to determine the shift for each position of the plain text. Okay, so that's what this says here in the overview. And I just have to stress again that this is a terrible encryption algorithm, okay? Don't use it for anything important, like not ever, okay? It's a terrible encryption algorithm. The reason that we use it is because it's easy to teach and it works like other substitution ciphers in some important ways, but it is not secure. Okay, so with that disclaimer out of the way, let's get going. So we're going to use Git to do everything. So you're going to clone the project from Git, and you're going to add myself and the TA as collaborators in Git. And what that'll do is it'll allow us to see your progress. If you have a question on your code, you can just say, hey, you know, I'm having trouble. Can you please check out my code and see what's going on, and so on and so forth. Okay. So what I want to walk through today is how to create your repository. Okay, so I'm going to open this, I'm going to go through these steps. Okay, so we're going to clone the repository and then change its origin so that it points to your own Git. Okay, so first we're going to go to github.umn.edu/new, and of course you have to log in. Okay, and now I need to pick a new name, and I'll call this Vigenère test. Okay, since this is just for this purpose. Vigenère Encraption lab. Okay, now it's very important that you make this private, okay, because we don't want your homework to be public. Okay, so you need to make sure that you set it to be public. I'm sorry, private. Set it to be private, and we do not want to initialize the repository. Okay, so then we click Create Repository, and it'll give us some instructions which we don't have to worry about. All we need to do is copy this URL. Okay, so again, it should look similar to github.umn.edu, your user ID, and then the title of the repository.git. Okay. So now what we need to do is we want to clone it and then change the origin. Okay, so open up a terminal window and find a place where you want to do this work. Now your MWA187 machines would work very well for this because it's Ubuntu, you have root access, so you can do anything you want. You can also do a lot of this work on Uko or Akka. Okay, so that's Uko, U-K-K-O, or Akka, A-K-K-A. And those are UMD machines, so uko.d.umn.edu or akka.d.umn.edu. Those machines might change, and so in the future there could be different machines. Any Ubuntu machine that has these utilities on it should work for you. You could also do it on your laptop, whatever works for you. Okay, so the main thing here is we need to git clone, and then the name of the, we need to git clone the name here. Okay, so basically what we've done so far is we have created a new account or a new repo, which is where you're going to put the data. And then what we need to do is clone our source repo to your machine, and then we're going to end up pushing it up to the repo that you just created, which is empty. Okay, so git clone this repository, and you're going to have to provide your username and password. And we've pulled it down. Okay, so if we cd into Vigenère, you'll see here is the base code that includes the Caesar code. Okay, so we don't have a Vigenère code here, we have the Caesar code. Okay, and so now what we want to do is remove the remote origin. So git remove git remote remove origin. Okay, and now we want to add in your original repository. So git remote add origin, and it's your repo URL from here. Okay. So now that you've done that, we can push our code up. So git push origin master. Okay. So now if I go and I look at this repo, my Vigenère test repo, I see I have the base code in here. Okay. Now you need to add the TA and your instructor as collaborators. Okay. So what you're going to do is click on settings for this repo, click on settings and collaborators, and then you can add me or your instructor if another instructor is using this, and you can add your, well, I already own this so I can't be a collaborator, and then you can add your TA's user ID here. Okay, and that'll allow us to see it and access it. Okay. Now let's talk about the assignment. Okay, so we're going to electronically grade your homework here. So we have a test script that's going to test to see if your encryption algorithm works properly by passing our tests. Okay, so it's very important that you use the code in the repository as it is. Use the scripts that are there, use the testing scripts that are there. That will tell you whether your stuff is working in the same way that our grading scripts are going to work. Okay. Your source code has to be submitted via GitHub. Okay, so we're not using Moodle to submit this code. It simply has to be pushed up to GitHub by the due date. Okay, and that means that you also have to have added the TA and the instructor. Okay, there's a list of banned functions that your code cannot use, and we'll talk about those in a little bit later. If your code uses any of those functions, you will get a 0. Okay, so there are some dangerous functions that have significant problems we'll talk about later in this class, but the main thing is right now you can't use them. You should use the safer versions of them. You need to create a single C source file that can generate both an encoder and a decoder. Okay, this sounds like a little extra work on the front end, and it is, but what it saves you from having is 2 separate programs, an encoder program and a decoder program. And the problem here is if you have duplicate code, you can have issues where you have a bug in one version of the code but not in the other. So it's just a recipe for disaster. So your code has to work in such a way that if you do GCC Vigenère C-O encoder dash capital D mode equals encode, that it creates the encoder, and the likewise for decoder, and it creates a decoder. There's some stuff in the appendix that we'll look at that tells you exactly how to do this, and it's kind of a cool thing to know about. Your code should not use any other libraries other than the standard libraries, so no Vigenère library or anything like that. Okay. You should not create any temporary files during encryption or decryption. Okay. There are some kind of bad ways that you might want to solve this problem with temporary files. That's not allowed. Okay. You shouldn't use any other online versions of the Vigenère Cipher as a coding template. Okay. If you want to read online about how to program in C and stuff like that, go for it. Absolutely. But please don't look for examples online about how to write a Vigenère Cipher or something like that. Keys need to be read in from a file. Keys need to be read in from a file name. Okay, so what that means is we're not typing in the key on the command line. But what you'll provide is a key file, and the file will have the key inside it. Okay, this is one of those things where if you don't do it this way, the grading script won't work properly. Okay. Keys need to be between 1 and 128 bytes long. Okay, so you only have to reserve up to 128 bytes for the key. All right. Keys may include non-printable bytes, okay, so non-ASCII symbols. That means you can assume that bytes might be random binary bytes and things like that, okay? And that's another reason for using a file, because it's hard to type some of those weird bytes that aren't printable, but we can put them in a file and use them as a key, okay? Input will not be limited to text only, okay? So we can encrypt, say, non-printable data like an image. Input won't be limited to any particular length, okay? So you can't assume, for example, that input is, you know, under a megabyte or something like that. It could be larger, and what that means is that your program should not work by reading the whole input into memory and then encrypting it, okay? So you have to think of a way that you can do it by encrypting small pieces at a time. Your main function needs to return 0 if it exits successfully. If the program doesn't exit 0, the script might interpret that as a failure or a crash. Your code also needs to use a reasonable amount of resources. So what that means is no more than 100 megabytes on disk, 300 megabytes of RAM, and 1 minute of CPU time and 100 subprocesses. You should never need 100 subprocesses or any of, you know, this size of memory or disk, but the important thing here is 1 minute of CPU time. If your encryption takes more than a minute, it's just going to be called a failure, okay? None of the encryption should take anywhere near that long, so if your encryption is that slow, there's something wrong with it, okay? Now, this code is going to be the basis for the next 2 encryption assignments. The next assignment, we're going to make a transposition cipher, a block transposition cipher, and then the third one we're going to make a product cipher. So you probably want to be kind to yourself here, document your code, put a little time into making it good because you're going to be working with it for the next 3 weeks, okay? Now your encoder and decoder take a number of parameters. So they take a path to the file containing the key. We already talked about that. So for example, the file might be named key file, and the file contains the characters monkey toast. Okay, that would be the key. The program also takes a path to an input file. So it's, for example, /temp/input, that would be your plain text, and a path for an output file, /temp/output. Okay, that would be the ciphertext produced by the program. And anything that exists there will be automatically written. Okay, so given that, upon running /encoder /path/to/key file, path to plaintext, path to ciphertext, what we're going to do is we're going to encrypt the plaintext using the key file and write it to the ciphertext. Okay, and of course decoder is going to do the opposite. Okay. If the same key file is used for encryption and decryption, then the contents of decoded might match byte for byte the contents of the plaintext, right? So once again, if you decrypt the data with the same key, the resulting plaintext, the decrypted ciphertext, should match exactly the initial plaintext, okay? There are some sample vectors, so sample inputs, along with correctly encrypted inputs and stuff are in the folders, so you can test with those things. There's a test script that will help you do testing and debugging, and you can see the README that's in the repo for information on that. Okay, so if I look at the README, there's some instructions for how to use the test script. Okay, in particular, you see that it says C test -H for special options, including a number of things. So if I do test-H, okay, it tells me a couple different steps and things that I can do. What happens if I run tests? Well, right now I only have the base Caesar code, so it fails, right, because Vigenère.c doesn't exist. Okay. Once again, for submission, we're just using GitHub. So you don't actually have to do anything to submit other than make sure that your code is pushed up to your repo by the due date and that you have added your instructor and the TA. Okay? All right, let's talk a little bit about how to read a file in. Okay, so how do I read a file key by key into a character array? Okay, or how do I read a file, for example, a key, into a character array byte by byte? Okay, here's example code on how to do that. Okay, So we have a character pointer which points to argv1. That's going to be the first parameter on the command line. And then we have a character array data, which has room for 128 bytes. Okay, and we have a unsigned int length and a symbol char. So a single byte is a char, right? And then we have this file pointer input. You'll see how we use that in a second. So we take the fopen function is going to take a path name and open it and return a file pointer into input. So what this says is if fopen input, storing the pointer into input, is null, that means there's a problem, it failed. So we say, problem opening the file, and we quit, exit 1, meaning with an error. Now if we didn't quit, that means this wasn't null, which means the open worked, so we're going to fall down here. And this is actually where we read the data. So we say while length is less than 128 and symbol equals fgetC input. FgetC is a function that takes an input from, takes 1 byte from the file, fgetCharacter, file get character, takes 1 character from the input, returns it, and then moves the pointer in the file forward so that the next time you read, you'll get the next character. Okay, so this says if we get a character for the input, we put it into symbol and it's not the end of file, then we want to add into data at index length the symbol. Okay, and then we increment length, so we'll read the next symbol. Okay, so that's how we can read the first 128 bytes into a file. Okay, if we wanted to read the next 128 bytes into a file, into our buffer, what we could do is just reset, do something with the data in data, and then reset length and read it back into the same buffer. Okay, so that's how you're going to want to do this for the encryption program, is not to create a buffer that's a megabyte large, right, because the file might be larger than a megabyte. Instead, create a buffer of a reasonable size, read the data into it, and then reuse that buffer for the next chunk of data. Okay, when we're done, we want to be kind and we close the file, and since just to show that we actually got the data, we can print out the data character by character and just print the data inside in our data buffer. Okay, so how can we use the key to shift characters, right? Remember that we're gonna in Vigenère we take a key, we kind of loop the key across the input, and then we shift each position of the input by the key. Okay, well, the nice thing here is that a char in C is an 8-bit integer. Okay, so you can essentially add 2 chars together to get the shift value, to get the new value of one shifted by the other, right? The thing you have to be careful about is to use modulo arithmetic and make sure that if the total of adding the 2 together is greater than 255, that it's going to loop back around to 0. Okay, so if I added character 255 by character 255, obviously that's going to be quite a lot larger than 255, and so I need to use modulo arithmetic to wrap it back around. Okay, now some students try to avoid, well, let me show you a little tip. Okay, so some students try to avoid looping through the key by like creating a huge buffer that's the size of the input and copying the key over and over into the buffer and then doing the shift. But what's easier and uses a lot less memory is to just have one buffer that you put the key in. Okay, so here the key is blorp, and the plain text buffer has endova bagarin in it, which is just a nonsense word. And here's our cipher buffer. Okay, so we have a key buffer that just has the 5 characters of blorp in it, and so we do our shift of B by A, and I just made up ciphertext here, so this is not a real ciphertext. B by A gives us X, let's say. Okay, so now we need to encrypt the next one, and so that's easy, right? We just do L by N, and we get, this, which isn't, again, this is just gibberish. Okay, and then we do O by D, and we get the next one, and then we do R by O, and we get the next one. And we do P by V, and we get the next one. So now what should we do? Okay, now we have to do A, but we don't have any more key. Okay, well that's easy, really. What we just do is we take and change the pointer in our key array, and we go back to the beginning. So we loop back around. So you have the key buffer, and then you'll have a key index variable, right, that's going to be updated as we go through the array, and then loop back around. So we'll do this and encrypt this, okay, and then for the next one, we'll shift to this character and this letter, right, and then this letter. Whoa, that's crazy. And then O and E, and so on and so forth. Okay, so eventually we're going to get down, RP, GA, and let's say we've encrypted these two, and now what do we do again? Well, it's easy. We just reset this index pointer back to 0, and then we do this one, and so on. Okay? All right. So, this talks about using the modulo arithmetic and how to do that. The band functions, so this is the last thing I think we have to, well, two more things to talk about. The band functions, so there are these functions that modify, copy, or do things with strings. Okay, so a classic one is strcpy. Okay, and what that does is that copies one string into another string. And in a C, a string is a character array with the last byte being a null byte. It's called the null terminator or null terminated strings. And the problem is that strcopy will copy any data until it hits a null byte. So a common error in C is that a string's null terminator disappears, and so then strcopy just copies off into memory random data that it's not supposed to, and that often causes your program to crash. So all of these band functions lack bounding. Okay, strcpy copies a file, a string from one buffer into another. strcat concatenates two strings together. strtok breaks a string into tokens. sprintf prints a string. vsprintf also does that. getS gets a string. strlen tells us the length of a string. All of these things will do that until they encounter a null terminator. So if your string for some reason doesn't have one, the program does some weird stuff and usually crashes. All the safer replacements have an N, so strncpy, strncat, and so on and so forth, where the N says, copy this string up to n bytes, and if there are more than n bytes, just quit. Okay, so you have to use the safe versions of these strings. Okay, and a couple other things to talk about. How do we pass build time parameters to GCC? So you can define values in your source code, and then when you compile the code, when you say -d mode equals decode, you end up setting the value of mode inside this compilation, and so then a different set of data will get compiled. Okay? So essentially we set mode as decode, and so then when the data is compiled, it says if mode equals encode, then we're going to do this, but since we said mode equals decode, we're actually going to include this code. Okay? How do we create files with non-printable bytes? The easiest way to do that is with a program called hexedit, which is a hex editor. Okay, hex is a way of viewing files in hexadecimal. So if we cd into source in our Vigenère, if I wanted to hex edit Caesar.c, this is what it looks like. So we see the index into the file here, then we see the data in hexadecimal, and then the printable data here. So if I hit tab and I go back and forth, so when I hit tab, I see I'm highlighted on the hashtag here, hash, and if I hit tab again, that's 23, and ASCII 23, sure enough, is the hash symbol. Okay, 23 in hex, I should say. Okay, And so what you'll find is there are times when it's useful to look at, say, your correct output. So if you look in the correct folder, you'll see these are the things that the testing script will encrypt. So this would be Abe Lincoln's picture, Abe JPEG, encrypted with key 1. Okay, so if we wanted to hex edit correct Abe JPEG encrypted with key 1, this is what the encrypted version of that file looks like. Okay, and so what you can do is you can say, okay, well, let's look at what key 1 is. Okay, because there's a keys folder. So hex edit key 1. Whoops. Keys key 1. Okay, the first key character is M for monkey. Okay, so that's hex 6D. Okay, and so that's hex 6D. We can also use the XXD program to just print a file in hex on the command line. Okay, so if I do XXD input abe.jpg and I do head, that prints the first 10 lines. Okay, I see that the first byte of abe.jpg is FF. Okay, that's not printable, so it shows up as a period here. So that's FF, and the first byte of the key is 6D. So the shift value should be these two combined, modulo, right, 256. So if I do XXD correct abe.jpg encrypt with key 1 head, we'll see that, in fact, 6D by 6F modulo is 6C, right? Because we lose one when we loop around this way, right? So, in fact, this is encrypted correctly, okay? So you can use that to debug if you think your program isn't working right. Well, you can figure out why, right? Maybe you can see that the key isn't looping properly, or only part of the input is encrypted. Okay, how can you compare two files? Okay, well, you can compare two files using diff. That'll show lines that differ. You can also use hexdiff. Okay, so hexdiff is a program that compares two files in hex and shows the differences. Okay, so suppose I copy correct abe.jpg encrypt key 1 into temp. I'll call it broken. Okay, and now I'm going to hex edit temp broken, and I'm going to change some hex values. Okay, I'm just changing some things randomly to FF. Okay, now yes, I want to save. So now if I want to see why my output differed from the correct version, I can do hexdiff, and I'm going to hexdiff temp broken with correct abe.jpg encrypt key 1. That's their source, right? So now, oops, hexdiff isn't installed, so I'm going to install hexdiff. And so what you see is on the top is the broken file, and on the bottom is the original file, and you can see all the different hex, the different bytes have been highlighted. Okay, so I can see where my file got corrupted. Okay, that's very helpful. Okay, so how can we perform decimal and hexadecimal arithmetic on Ubuntu? It's easy. Just open up the GNOME calculator, which you can get to in Ubuntu by searching for calc, and you want the calculator. Okay. So under GNOME calculator, we want to switch to from basic mode, which is probably where yours will start, to programming mode, and then you can switch from decimal to hexadecimal. You can also do that using Control D and Control H. Okay, and so we can actually show how to do a Vigenère shift. So remember, here's keys 1. Okay, and the first hex byte of that is 6D, so we can do 6D, and we're going to shift that by the first byte of that's key 1. So we're going to shift the first byte of the abe image. So here's the image abe file. We're going to shift the first byte by FF, so 60 plus FF. Okay, and then again that has to be modulo 256. Okay, and 256, so FF is the highest we can get in 8 bits, but 256 is more than 8 bits. Okay, so 256 would be mod 100, and if we hit enter, we see that the answer is 6C. And if you look here under correct abe encoded, the first byte is in fact 6C. Okay, so when you go through your output, if you have an error, you can figure out what the error was by looking at the math and thinking about, well, okay, if this wasn't 6C, if it was something else, you know, how would I have gotten that? What if it was 6D? Okay, if my output was 6D, well, it turns out that 6D plus FF, okay, mod FF is 6D. Okay, so you'd be like, aha. So I moduloed by 255 instead of by 256. If I mod by 256, I get the right value. If I mod by 255, I get the wrong value. Okay, so GNOME calculator plus hex editor. So again, hex edit is an editor for hex. Hex diff shows the difference between 2 files in hex, and XXD prints out a file in hex, and you can use head to limit how much to print. So head by itself will do 10 lines. You can also specify the number of lines. So here we do 2 lines. Okay, so that's how you can do arithmetic in hex and decimal on Ubuntu. All right. If you have any questions at all about this project or anything else, please contact your instructor or your TA. Thanks.